Recording is rolling. Welcome to Wednesday, December 8th. Gonna have you guys finish this lab today, but let me get you guys started here, give you guys a few tests at the front. So, you guys remember yesterday you started this lab where you had this weight tied to this central post around this T-shaped pipe system that, when the weight would fall, this induced spinning. And you're trying to figure out what is the rotational inertia of this T-shaped system. Remember, the more rotational inertia it has, the less it will accelerate spinning, the less angular acceleration it would have. Okay, right? So, how are you going to do that? Remind you guys how this lab's going to go together, but I'm going to explain this backwards of how I explained it yesterday, working from the end. Okay? So, an alternate solution to this that I think I mentioned yesterday was you could actually model this with, it's pretty similar to one of the classic shapes in the textbook on page 257 for rotational inertia. You guys remember, say, a pipe spinning about its central axis here ends up being 1/12 ml squared? I ran that calculation myself this morning. So I grabbed what is the mass of one of these arms, 152 grams, double that for the mass of this whole thing, turn that into kilograms, right? Divided by 1,000. And then end to end, this was 1.25 meters. So if you pop in those numbers, 1/12 ml squared. This is the number I got using that approach, which is different from what you guys are doing. You guys are doing this empirical approach through torque and angular acceleration, but using this method, I got this number. So when you guys figure out the rotational inertia using your method, it should be pretty close to this, kind of in that ballpark. Right. So the way you guys are gonna figure this out is with a tau versus alpha graph. So remember, this would be the last couple of steps that you guys do. You guys put together this graph, and then the slope of this graph would tell you rotational inertia because tau is equal to I times alpha. That's analogous to F equals ma. Okay. Notice I said tau net, like a net torque. Okay. Kind of like net force is equal to mass times acceleration. Okay. And that detail is important. I mentioned yesterday that your graph is probably going to have an intercept here. Probably have some like tau naught, like y-intercept sort of. Right? Have you guys been able to figure out between yesterday and today why I think you're going to have an intercept, or why that should probably be the case? So, critical thinking kind of question. Huh. How about this? What if, in the setup, you put on a really tiny lab weight, like this one right here, like real small, and it just stayed at rest and it didn't even move it? Huh. That could happen, right? Maybe if there was some friction. I mean, this pipe spinning around, it is like pipe touching pipe. There is some friction going on, right? Okay. Hey, do you think you might need a minimum amount of force, minimum amount of torque to induce rotation at all? Okay. That's what this would be. So at 0 radians per second squared, you need some minimum torque to overcome the frictional torque. That's what this represents, the frictional torque. Okay? And then anything after that is what counts towards making it rotate. Okay? Because after that, it doesn't matter how fast it's spinning or the rate it's spinning up. The frictional torque is just going to be that constant value, that tau naught. Right? So it plays like that. Right, now, that's near the end of the lab. But what are the steps that lead up to that? Okay, so, and this is my thought process putting this lab together. And it's also a good thing you guys should be able to do yourselves, is because ideally I'm supposed to say, figure out the rotational inertia, go. And then you have a blank piece of paper and do this whole thing from scratch. So, like, can you work backwards from knowing what you're trying to figure out? Well, using this method, you need tau and alpha. AP really likes graphs a lot, by the way, just like I like graphs a lot, so they could totally want you to solve it this way. Okay? So how are you going to get tau and alpha? That's the last two columns on this table. Okay? Well, tau torque, that's R cross F. Okay, so you could directly measure radius. That's one of your first columns. Okay? But then, that force, well, that's represented by tension, because if you zoom in on the system, here's the some tension force at some radial arm distance. This R across this F is what's inducing that rotation. So if only had the tension in that string, how are you going to get the tension? It's probably pretty close to the weight of that hanging lab weight, but a little bit less. Why a little bit less? Because it's accelerating down. So that comes from m times g minus a, but that was actually derived from, you'd have to set up a free body diagram, do a little bit of algebra. I took you guys through these steps yesterday, just to remind you guys that it looks like tension in an elevator cable if it's accelerating down. Stuff like that. Okay, you can get M, and G is like 9.8 meters per second squared, so you can assume that. But what is that A? What is the linear acceleration of that lab weight? Huh. Okay. Well, that might have to do something with how far it's fallen and how much time. Hey, do you guys remember that college equation? X equals 1/2 AT squared, as long as you start from rest. Rearrange that and solve for A. That's how you do that. So acceleration is 2x over t squared. It's just the college equation rearranged. Okay? So measure x, measure t to go that distance x, and there you go. One last detail. How exactly do you get alpha, the angular acceleration? Because that's linear acceleration divided by the radial size. That is, where'd my, here it is. Okay. You guys remember how to connect rotational kinematic and linear kinematic values? Okay, just multiply or divide by r, depending which way you're going. Okay, so if you want to know alpha, just take linear acceleration of the weight falling, divide by the radial size of the pipe, and that would tell you how fast it's speeding up spinning. Okay, like that. Okay, and at that point, you got everything you need. So there's the explanation backwards. Yesterday I explained it, how you do it forwards. One last detail here is the last 10 minutes of class today, I'm going to bring you guys back together and make sure you have this lab write-up done on the back by the last 10 minutes of class today. I'm going to have you guys score yourselves out of 12, created a 12-point rubric. Okay. Also, it said one last thing, but I forgot about those. Yeah, it's always one more thing. So tomorrow I'll start on the midterm review with you guys. We'll take a few days to do midterm review. I'll make sure to give a really comprehensive review. The midterm itself is going to be a bunch of multiple choice, but also a couple of free response. But I'll make sure that I ask you guys something that's covered in the review. And your very first exam is going to be next Thursday, and that will be for period 7. Okay? I am not going to be at school that particular day because I have jury duty. Here's my jury summons. Just so you know, hopefully this is just a one-day thing, but just want to let you guys know that that's what's going on my end. Okay. So go ahead and take some time and finish this lab. Make sure you do the graph, get the value for I, and then make sure you do the lab write-up. And last 10 minutes of class, I'll go through the paper rubric with you guys.